If you insert a dielectric between the plates, you will increase the capacitance of the capacitor for the same area, for the same separation. But now, when we have dielectric rather than vacuum, we will increase the capacitance. We introduce a new quantity. We call it the dielectric coefficient, kappa, which is the ratio between the voltage when there is vacuum to the voltage after we insert the dielectric. And the capacitance with the dielectric is simply kappa multiplied by C naught. Kappa is a Greek letter. So C naught is the capacitance when the medium between the two plates was vacuum or air. And now, after inserting the dielectric, the new capacitance is kappa C naught. Kappa is always greater than 1. You will see in your textbook this a list of the dielectric constants kappa for various materials. As you can see, for air, it is similar to vacuum. Okay, for vacuum it is 1, for air it is 1.0059, so the same thing. For water it is 80. For silicon oil it is 2.5. For fused quartz it's 3.78. So as you can see, we can increase the capacitance by filling the space between the two plates with the proper dielectric. So this is the equation. When there is vacuum, it is epsilon naught A over D. When you insert a dielectric, it is kappa multiplied by that capacitance. This is another example of the discharge of a capacitor. When you charge a capacitor and connect it to 3 electrodes like this, if the potential difference between the plates is high enough, if the energy was high enough, then you will have a spark here. You will have a spark, okay? Capacitors are fabricated in all forms to serve all kinds of applications. This is here the tubular capacitor. You have two conducting plates separated by an insulator, like a piece of paper here, and we just wrap it this way. We call it paper capacitor or tubular capacitor. This is another capacitor which uses oil as an insulator. This is important in high voltage applications like in nuclear physics and accelerators. This is a third form where you have a chemical inside. We call it electrolyte capacitor. Electrolyte capacitor. You use titanium dioxide here to boost the capacitance 100 times or more. Here you see several forms of capacitors that are available commercially in the market. These are electrolyte capacitors. They have polarity. They have chemicals inside in order to boost the capacitance. These are called ceramic capacitors. The insulating material is made of ceramic here. Here you see some tubular capacitors, paper capacitors. This is a variable capacitor used in communication equipment. You have two sets of plates. This is fixed. This is movable. When you rotate this knob, eventually you are increasing or decreasing the effective area between the set of plates, the movable and the fixed plates. So we vary the capacitance by varying the effective area between the two sets of plates. A fully charged parallel plate capacitor remains connected to a battery while a dielectric is slid between the plates. Does C increase, decrease, or stay the same? We know that when we insert the dielectric, we increase the capacitance. A fully charged parallel plate capacitor remains connected to the battery while the dielectric is slid between the plates. Does delta V increase, decrease, or stay the same? Delta V depends on the field, and the field depends on the dielectric, but the net effects here, it remains the same. We move to another important topic, which is the electric dipole. This is the water molecule. There are 2 hydrogen atoms and 1 oxygen atom in the water molecule. The equilibrium structure for the water molecule is like this. There is an angle of 105 degrees between the bond with this hydrogen atom and the bond with the other hydrogen atom. So now if you take the center for the positive charges in the molecule and the center for negative charges, they will not overlap. For oxygen, there are 8 electrons, 8 protons. For hydrogen, there is 1 electron, 1 proton. For hydrogen, there is 1 electron, 1 proton. Together, we have 10 electrons and 10 protons in the molecule of water. But the center for the negative charges is different from the center for positive charges. Because of that, you have a situation with 2 charges, one minus 10e and plus 10e separated from each other. Therefore, you have an electric field between them. This is called an electric dipole. So water molecules have permanent dipole due to the distribution of the negative and positive charges in the molecule. Under the influence of an external electric field, positive charges will move with the direction of the field, negative charges will move opposite to the field. So even if a molecule does not have a permanent dipole moment like water, like here you have this symmetric dipole, when you act by a field, the center of the negative charges will move opposite to the field, while the positive charges will move with the direction of the field. So again, you induce polarization. So the dipole that was neutral before the field, now the dipole has this polarization, has this shift between the negative and positive charges. On a large scale, if you consider the behavior of any dielectric under the influence of the electric field, this is without the field. And then when you apply the field, the molecules will reorient themselves. The positive ends of the molecules will be aligned with the field. The negative ends will be aligned opposite to the field. This leads to producing a net induced field. A net induced field, when you add the field here, the field here, the field here, when you add them, you will get a net induced field that is opposite to the original field. Therefore, as you can see here, the result of inserting a dielectric inside a capacitor, it leads to reducing the net electric field. The unit field is equal to E naught minus E induced. When E decreases, C increases. So now we explain, we understand how the dielectric leads to increasing the capacitance, because it simply reduces the net electric field. We are done with this chapter. To recap, we learned about the similarity between electric potential energy and gravitational potential energy. we introduced a new quantity which we call electric potential or voltage, which is potential energy per unit charge. We compared the new quantity, the electric potential, to the electric field. This is the electric potential KQ over R. This is the electric potential energy for two charges, KQ1, Q2 over R. We introduced a new quantity for energy, 1 electron volt, 1.6 by 10 to the minus 19 coulomb volt, or 1.6 by 10 to the minus 19 joule. Then we introduced capacitors and defined capacitance as the ratio between Q and delta V. We calculate capacitance from this equation, ratio between Q and delta V, or mathematically from A over D multiplied by epsilon naught, the permittivity of free space constant. Then we learned how capacitors are wired in parallel and series. In parallel, just add the capacitors to get the equivalent capacitance. In series, you take the reciprocals, add them to find the reciprocal of the equivalent capacitance. Then for the energy stored in a capacitor, we can calculate it using one of these three formulas, half QV or half CV squared or Q squared over 2C. When we insert a dielectric, the capacitance is increased by factor kappa, the dielectric constant for the material.